And I will introduce our speaker. So we are very happy to have Dr. Paul Rimmer with us. Unfortunately, he can't make it in person today. He did his PhD in 2012 in astrochemistry, I would say, typically ISM things, with Eric Herbst, which is one of the popes of astrochemistry at Ohio State University, which is in the US. Then he moved to Christiane, to the LEAP group, and he was a postdoc there for 4 years. And there he developed this so-called STAND network, so that's for St. Andrews. And it's a very large and one of the most, I would say, ambitious astrochemical networks, has all kinds of things in it. And there's always current work on this network itself. And then he also developed the Argo program, which is a modeling program for the atmospheres of planets. And he applied that successfully to Earth, to Mars, to Venus, to Jupiter, and then also to exoplanets. And actually some of our group members here are working with this code together with this network. He is also an expert in cosmic rays, so he has worked on this together with Christiane concerning the effects of cosmic rays in the upper atmosphere. And then in 2018, he won a big grant, this so-called Simmons Senior Fellowship from Simons, which allowed him to go to Cambridge, where he's now an assistant professor in experimental astrophysics. So he built up the STAR, what's called the STAR Lab, and he just mentioned to me that it's now up and running. So where they can measure, for example, UV photochemistry processes. And he also became, say, from a more astro person to an astrochemistry biologist, because he's now studying these kind of pre-biosignatures. And we will hear more about this. So you see the abiotic baselines, kind of, what to expect when, on top of which only then you can make a claim for a biosignature. So in Cambridge, there's now theoretical chemistry work and experimental simulations going on for several things: atmospheric physics, volcanic eruptions, impact-generated chemistry. And this is ongoing work. Since 2018, he is also in collaboration with Prague, with the Department of Spectroscopy as a guest professor there. And we submitted a common application, which unfortunately failed, but we will resubmit. And since 2021, and this is particularly interesting here, he is part of the science team for the Venus Life Finder mission, which is a privately funded mission. It's a rocket that will be launched and it will go to Venus and collect samples. So this is organized by the MIT. So it's US, but it's not NASA, it's privately funded. This is what I found. And so I think today we will hear more about his models for Venus and maybe also connected to this life finding mission. Okay, Paul, take it away.
Thank you very much, Peter, for that kind introduction. I'm really looking forward to talking with you about Venus. Part of this talk will be a little bit autobiographical. Just talking about how I kind of got involved thinking about Venus, the particular issue that first interested me about it, and then where I ended up going in this respect. I found a whole bunch of other interesting things about Venus that I've now started to explore. So Venus is our nearest planetary neighbor. It's interesting from an exoplanet perspective in that in terms of most of its characteristics, it would be considered identical to Earth from an exoplanet's from an exoplanetary vantage. It's roughly the same size, it's roughly the same mass. If you could directly image it and get its brightness temperature, it's actually a little bit cooler than Earth in terms of its brightness temperature. And that's because the temperature that you're probing is high up in the clouds. But as we know, it turns out Venus is very, very different from Earth, and especially in ways that matter for questions of habitability and the search for life. So on one side is a picture that I took of Venus, Jupiter, and the Moon when cycling home with my son. And on the other side is a slightly better picture. I believe that one is from the Magellan probe, and that is in the UV. So you see these beautiful contrasts in the clouds when you look at Venus in ultraviolet light. I have a lot of collaborators. It turns out looking at planets is a multidisciplinary endeavor, and this involves a lot of different disciplines and a lot of different areas of expertise. And I will highlight the collaborations with most of the people shown here in later slides. So first, I'm going to talk about a historical vision of Venus. This is from New York Times, 1928. I got these slides thanks to David Grinspoon. A particular professor who knew how to balance brightness temperatures but didn't yet know about greenhouse gases made an estimate about what the surface temperature of Venus should be like. If you just look at thermal balance and assume a certain albedo, you can find out that Venus is actually quite temperate. Predictions of liquid water on the surface. A lot of this kind of speculation inspired some great science fiction, including Isaac Asimov's Lucky Star and the Oceans of Venus, and a variety of other books and old science fiction movies. However, it turned out that this picture was inaccurate. Later New York Times article titled "Venus Says No." This is in 1963, and this is when we ended up actually getting a more definitive picture. The surface of Venus, it turns out, is at around 740 kelvins. It was hot enough that actually one of the early Russian probes that was sent carried a bust of Vladimir Lenin. And now that particular bust is a puddle on the surface of Venus somewhere that's probably artificially enhancing certain metals in that particular region. But this didn't stop speculation about life on Venus, because it turned out that the clouds of Venus are at around 1 bar pressure and around room temperature. And this would be really, really good for having liquid water clouds. That was the speculation at the time, is that the clouds were made of liquid water. And there was some speculative work by Harold Morowitz and Carl Sagan. A good example of collaborative work between astronomy and biology, speculating about how you might have life that was sustained just in the clouds. There's also a nice book about the clouds of Venus by David Grinspoon. Well, this also ended up getting spoiled a little bit, because it turns out the clouds are very, very likely made out of sulfuric acid. And even if not sulfuric acid, something with a very significant component in the liquid phase of sulfuric acid. This shows Joanna Barstow's early retrieval work, estimating the acid concentration as a function of depth. As you'll see, this is 1.74 micron radians, which is inversely proportional to the optical depth. There wasn't a very nice picture in the paper that I could find relating this specifically to atmospheric height. But the sort of picture here is that, and you can't quite see my pointer, but if you look at the 0.05, that's deep in the clouds, and the 0.25 is near the top of the clouds. And so you see that the amount of sulfuric acid goes down as you get to the top of the clouds. That'll become important later. But you're still talking about sulfuric acid concentrations of somewhere between 75% all the way up to 90, 98%. But you can still speculate, well, maybe you have life in sulfuric acid clouds. And so Dirk Schultz-McCuish and co-authors proposed a sulfur-based survival strategy for putative phototrophic life in the Venusian atmosphere. And there's been a lot of other, this is just one example of several papers that have speculated on life in the clouds. And I should also just emphasize, we've been to Venus quite a few times, although not for some time, and certainly we haven't sent anything into the atmosphere of Venus since the 1980s. Many of these missions, as you'll see, are Russian missions. There's a whole bunch of Venera missions, which involved atmospheric probes and various landers. Venera 8 was the first successful landing on another planet. And then going all the way out to the first American mission that went into the clouds was Pioneer Venus, which had two components, an orbit. There were the later Vega missions, which involved an orbiter, an atmospheric probe, and a lander. And then there's Akatsuki, which is a Japanese mission. That's purely in orbiter. It's getting fascinating data about some of the physical properties of the clouds. Well, in the late 2010s, Jane Greaves happened to observe this 1 millimeter feature in the clouds of Venus, which she and others attributed to phosphine. This is a picture of that particular feature, which you can see at Venus frame velocity of 0. I won't go into a lot of detail about this here unless you have questions about it, and then I'll be very, very happy to discuss some of the details about it. There are some major questions about whether this feature is even a feature, whether it's actually there, and if it is there, whether it's due to sulfur dioxide, or whether it's due to phosphine, or whether it's due to some unknown chemistry, some unknown molecule. And then if it is real, where is it located in the atmosphere? And is it actually in the clouds, or is it above the clouds? And I think that there's been some consensus now that both the feature is real, and it's largely above the clouds. There's no consensus about anything else about this. But this is where I started. So I started looking at this and thinking about phosphine in the clouds of Venus. I started looking at phosphine on Earth. It doesn't survive hardly at all, thanks to water photochemistry. You get these hydroxyl radicals that just eat it up really fast. But it turns out that in Venus, it survives a lot longer, and so it seemed a bit more plausible. But when we really started digging into the details, it was very, very hard to find any way to form this without just throwing in a huge flux of phosphine, a flux that is comparable with some of the estimated fluxes of phosphine in certain environments on Earth. Of course, if it's above the clouds, and this is something we can talk about later, but if it is above the clouds, you would need fluxes that would be larger than any fluxes, biotic or abiotic, that we would know of. We argued at the time, and I still believe this, that the best candidate molecule that we know of would in fact be phosphine itself. But this, of course, does not rule out the unknown. It's very, very difficult chemically to explain why phosphine would be there. You can ask me later why I'm still fairly convinced that this feature is not due to SO2. And it largely deals with just the amount of SO2 that happens to be there based on contemporaneous measurements. And this is something I'm also uncertain about, and I think a lot of the community is uncertain about, but it is interesting. Rakesh Moghul looked back at the Pioneer Venus mass spec data and found features that are consistent with the presence of phosphine at about 51 kilometers. You can try to get abundances out of this, but abundances out of such low resolution mass spec are notoriously unreliable. But the sort of interesting thing is this is not the only thing that's been claimed to be in the atmosphere based on mass spec data. Here's a picture of a whole bunch of different molecules that have been claimed. O2 in the clouds, ammonia in the clouds at part per million quantities. Methane in the clouds was claimed from Pioneer Venus data in thousands of parts per million quantities. There are these strange mode 3 particles, these large non-spherical particles that seem to be near the bottoms of the clouds. There's been X-ray measurements from the Vega missions that see a lot of iron in the clouds, and some of the measurements, but not all, see large amounts of phosphorus near the bottoms of the clouds, with phosphorus being about as abundant as sulfur. And I'll get to a full picture of the atmosphere of Venus in a little bit, but having as much phosphorus as sulfur would be quite extraordinary. And this comes from a paper that's under review. It's, I believe, very close to being accepted. Petkovsky et al., Astrobiological Potential of Venus Atmosphere, Chemical Anomalies and Other Unexplained Cloud Properties. Oh, and of course, there's this strange UV absorber. We don't know how to explain that either, and I'll touch on that near the end. So why is pH3, or for that matter, NH3 or CH4, why is this so strange? And this has a lot to do with the oxidation state of the phosphorus and what you would expect the oxidation state to be from chemical equilibrium. A lot of this is based on models that Shannon Fisher ran in and published in 2006, and some follow-up work that William Baines has done looking at the equilibrium chemistry. So it turns out that if you're in a hydrogen-rich atmosphere, phosphine, in fact, is not all that unexpected at all. In a large region of parameter space, including deep in Jupiter's atmosphere, it should be the most abundant phosphorus-bearing species. And that should transition, if chemical equilibrium is respected, to what's called phosphorus trioxide. You'll see that's not really phosphorus that's not what I would call phosphorus trioxide by the name, but that is the historic name of that particular species. It's 4 phosphoruses bound with different oxygens in this polygon shape. It turns out actually you do see phosphine higher in the atmosphere of Jupiter. And the reason that you see it higher in the atmosphere of Jupiter is because of chemical quenching. So deep in the atmosphere of Jupiter, hydrogen rich, you expect to form a lot of phosphine. There's a lot of hydrogen around to bond with your phosphorus. That molecule is stable enough that when it gets dredged up to where the temperatures are colder, there's not enough energy to break the bonds anymore. And so you still end up with a lot of phosphine there. But thermochemically, you would expect this P4O6. On Venus, on the other hand, because there's almost no hydrogen, it's very desiccated, you would expect a lot of this phosphorus trioxide deep in, and you would expect phosphoric acid higher up. This is from chemical equilibrium. So, and phosphine has been claimed as a sign of life on Earth and potentially on other exoplanets or other planetary systems, so long as they have fairly neutral to oxidized atmospheres. It was claimed as a sign of life on Earth by Glendeman in the 1990s by a series of papers, and by Clara Souza Silva in 2020 for certain rocky exoplanets. But the probes haven't just found a whole bunch of weird things, including reduced things. They found other weird things that have nothing to do with redox chemistry. One would be with SO2. This is largely based on the Vega data. So Vega were probes that were sent down. What you would expect is you would expect, actually, all things being equal, SO2 should be fairly well mixed in this kind of atmosphere. Maybe you would expect some depletion in the clouds because the clouds are made out of sulfurous species. But you actually see depletion near the surface. This has never been well explained. And in fact, lots of people don't really believe this. But that is what is observed by these particular probes. With water, water is also kind of interesting. There's a whole bunch of even contradictory information about water in the clouds. As you can see below the clouds, and largely above the clouds too, with more modern data, it all seems to converge at around 30 parts per million. There's wide agreement from ground-based observations that go way past 1997. But in the clouds, you notice all of these strange data points, and a lot of these come from the Venera and the different Vega missions. And in fact, the Vega missions had two different ways to detect water. Some of them involved chromatographs, and some of them involved looking at spectral signatures, and the spectra got one answer and the chromatographs got another. The spectra got answers in the hundreds of parts per million, so still an order of magnitude larger than what you see below the clouds. But the chromatographs got answers into the thousands to almost 10,000 parts per million. And this is also confusing. It's very difficult to reconcile all of this data. This is what I've already mentioned. Vega's X-ray radiometer sees chlorine, sulfur, phosphorus, and it does see iron. I've never been able to figure out why they've never shown the plot for iron in this particular paper, but I do have a paper that's, as far as I can tell, has never been translated from the Russian that has just the iron data and none of the chlorine, sulfur, or phosphorus data. But there's a fair amount of iron, and the amount of phosphorus is comparable with the amount of sulfur. But as you can see, the phosphorus goes deeper into the clouds and the sulfur is higher up. And I should also emphasize that there were two Vega probes. Vega 2 saw the phosphorus and the sulfur. Vega 1 only saw the sulfur. So either there's transient phosphorus or something happened with the X-ray radiometer with Vega 2. So now I'll just describe a little bit about what we know about the atmosphere with the things that we're more certain about, and getting into the things that we're less certain about as we go. So Venus as a planet has about a 100 bar surface pressure and about 740 Kelvin surface temperature. Its atmosphere is made predominantly of CO2. It's about 97% CO2. The other 3% is nitrogen. So it has a very, very large amount of nitrogen in its atmosphere. And then all the rest are trace species. It has a lot of sulfur compared to the amount of sulfur, for example, that's typically available in the atmosphere on Earth. It's 150 parts per million SO2. And we can actually start drawing some of these. So there's CO2, which might need to be replenished from the surface. There's SO2, which might also need to be, released via volcanism or produced by some surface processes. And there's a bit of water, as we said, 30 parts per million. Right now, I'm going to be assuming that the SO2 does not deplete near the surface. CO2 will diffuse up, where it will dissociate into CO and O. SO2 will also diffuse up, where it will dissociate into SO and O. So you have a fair amount of atomic oxygen at the top of the clouds, thanks to photochemistry. And that O can attach to the SO2 to form SO3. Water also diffuses up, and it can react with SO3 to form sulfuric acid, which will then condense out, and it forms some of the clouds. And the water will get absorbed into the sulfuric acid, and so the water will also deplete. You also have OCS at around 1 to 10 parts per million near the surface. You also have HCl at around 1 part per million. OCS will diffuse up and it will photodissociate into CO and S, which will quickly find other sulfurs to make sulfur allotropes, which will then condense out. OCS near the surface can also dissociate into S and CO, and some of those sulfurs will also make sulfur allotropes. But some of those will react with HCl to produce hydrogen sulfide, which will diffuse up and dissociate and make more sulfur allotropes. SO can also make more sulfur allotropes. There are a variety of ways to get that. HCl can also go up, and there's a whole thing that happens with chlorine chemistry I'm not going to go into, but it helps to moderate the amount of O2 in the upper atmosphere. There's geochemistry, almost certainly, that has to be going on in order to balance out and keep the atmosphere long-term stable. And there's a bit of a puzzle, and this is what I'm going to be highlighting, between the SO2 and the H2O. And again, there might be phosphine in the clouds. The puzzle is this. So the way that you would make sulfuric acid is you would photodissociate your CO2, and the oxygen that you get reacts with your SO2, and that makes H2SO4, which then condenses out. So overall, it's one SO2, one H2O, and one CO2 make one molecule of H2SO4 and CO. But the problem is that the SO2, as I mentioned, is 150 parts per million, and the H2O near the surface is 30 parts per million. And so if we take that seriously, there's a factor of 5 difference. You might say that most of your oxygen comes from just more SO2 dissociation, but that still wouldn't make up enough of the difference. There has to be some other way that the SO2 is being removed. So how is the rest of the sulfur removed? And so one of the things that I and colleagues, including Sean Jordan, Teresa Constantino, Peter Wojtka, Oliver Schwartl, Richard Hobbs, and Alyssa Paschaldamas, all proposed. We ended up looking into whether there might be salts in the clouds, and whether these salts, if they were produced from hydroxides, the hydroxide could get into the clouds, help to buffer the clouds, and could end up taking in extra SO2, forming sulfites, and maybe somehow those sulfites can get oxidized to sulfates. This is kind of a way of smuggling hydrogen into the clouds so that it can continue to do the sort of chemistry without the hydrogen showing up in gas phase species. The way that we ended up modeling this is with a photochemical model, which many of you have had some experience with. This is the Argo model. It's a Lagrangian solver for coupled nonlinear differential equations. It has production and loss terms. So this is the change in the number density of a species as a function of time. That's what the nx over is the number of species x. That's the production of that species minus the loss of that species. The production is in terms of molecules per centimeter cubed per second, or atoms per centimeter cubed per second. The loss is in terms of molecules per second times the number density. And then you have this vertical transport as well. This calculates also UV transport in the atmosphere, and it iterates between the UV transport and the chemistry until there's convergence. Or until it's gone through a large number of global iterations and has not converged, and it will tell you that. Under most circumstances, it can converge for these sorts of planets, and all the results I'll show are results that have converged. It involves, and I should update these numbers, but it involves thousands of reversible reactions, hundreds of irreversible reactions, involving hundreds of species made of HCNO, SCl, and a handful of other things, including phosphine was added in to just see what happens if you throw phosphine in there. But the phosphorus chemistry is pretty much just phosphine and pH 2. So photochemical models need inputs. In this case, this is the temperature profile that we use, which we got from Vladimir Krasnopolsky's 2010 paper. We also got We also used his eddy diffusion parameterization from that paper with some deviations, which you'll see drawn on there. But all the results that I'm showing in this talk involve just the solid black line, which is the same as Krasnopolsky's values that he used. And we use these mixing ratios, which seem to agree best with the sort of community consensus of what the surface mixing ratios of these species should be, and is actually fairly close to what you would expect from equilibrium abundances, which is something you can also ask me about later, and something which we talk about in the paper as well. So the idea of the sulfur depletion is that you have your SO2 from the gas phase, which then goes into the liquid. So you have SO2 in the liquid, which can then react with whatever water happens to be in that liquid, which will then dissociate and form bisulfite. And the bisulfite can also make sulfite, although there's very little of that at such low pH. Sulfate, it's the same sort of thing. H2SO4 itself, a lot of it is in bisulfate. The really key ingredient is the very last step there, which is that we throw in some sodium hydroxide, which breaks up into sodium and OH minus, and the OH minus connects with the abundant number of protons there to make H2O, which then can react with a SO2. And this allows you to sequester SO2 into the clouds. And so here are the results that we get from our photochemical model. We also tried different solutions, low SO2, high H2O, basically making those ratios a little closer. We found some ways to get those to work, but not without creating other problems for fitting with observations. It makes predictions that don't quite fit with observations as well. So what's shown here, and unfortunately, oh, good. Yes, both X and Y axes are there, but the Y axes are on top. I'll just point that out. That's mixing ratio and atmospheric height. The clouds are around 48 to 60 kilometers. And so what you can see is that the SO2 does deplete when you use this sort of cloud chemistry fairly well. You have a fairly low amount of O2, especially compared to the fiducial case, which is the black line, which is not putting in any of the sort of chemistry and just running with what we have. You get a lot more O2. O2 is really a problem, and you also don't explain the SO2 depletion at all. You get a little bit of H2O depletion. You can get more if you play with the eddy diffusion constant. CO fits fairly well for most of the models. And again, H2O fits fairly well once you include the cloud chemistry. But this is because we tune the amount of sodium hydroxide so that it best fits these sorts of observations. And then what you can do is you can say, well, given the sodium hydroxide that I added in, what would that do to the cloud pH? And it turns out it neutralizes the clouds, brings them up to about a pH of 1, which itself is very interesting because it opens the door for all sorts of other kinds of chemistry. So one of the questions we can ask is, what is the base that then becomes the salt? We considered hydroxides. Sodium hydroxide actually can't work. The main reason we used it is just because it has fairly well understood kinetics. So we know the kinetics are very fast, and most of these have fairly good constraints on their thermodynamic properties, at least. But the sodium hydroxide doesn't work because it's not stable near the surface. Calcium hydroxide would be stable. In fact, just calcium hydroxide is very stable at the surface temperatures of Venus. It does turn out, though, that in the presence of CO2, it will react away, forming carbonates and various other things. But that reaction is at least somewhat kinetically inhibited. So if you could quickly move your calcium hydroxide up, it could work well. Iron and magnesium hydroxides are also unstable, unfortunately. There might be other hydroxides, more exotic ones that we could consider. And I'll be talking about this a little bit later, but what about sulfates? Maybe there's just a way, since we know there's iron in the clouds, or we think there's iron in the clouds, there might be a way to make sulfates out of them. Ammonium sulfate may be possible, but it's hard to explain without active biological redox chemistry. I'll touch on that a little bit. And like I said, iron was already observed in the droplets by at least 3 probes. So both of the Vega probes and the Pioneer Venus probe see signs of iron. So what about iron sulfates? And that's one of the things I'll be going into soon. But first, I'm going to talk about the ammonium sulfate a little bit. What if the sulfur depletion was in fact due to life? There might be ways in which this would work with the ammonium sulfates that would actually work out well. And I would point you to a nice paper in PNAS, first author William Baines. We look into the implications of this for the clouds, but we don't really take into account a true metabolism. If you actually do try to take into account a metabolism, this is work that one of my PhD students, Sean Jordan, has done. This was published in Nature Communications. And he considers some possible metabolisms from the literature. A, B, and C. A is taking hydrogen sulfide, reacting it with SO2 to form various elemental sulfur and H2O. And this uses light. B is one that uses hydrogen and CO, and it uses chemical energy. And C just uses CO as its as a source of chemical energy. All of these favor thermochemically the products, and so there's chemical energy to be had here, and so you might expect life to use these. What Sean Jordan did is he applied fluxes of these sufficient to explain the SO2 depletion, and found out what else happens with the chemistry. How big do the fluxes need to be from the biology to remove the SO2, and then what else happens to the atmosphere? And as it turns out, you can, in fact, get your SO2 depletion if you make the fluxes big enough. That's not a surprise because that's our free parameter. So you have the fiducial, the in-droplet chemistry, which was what I showed before, and then metabolisms A, B, and C, which involve these various fluxes. To get the SO2, it turns out that for most of these, you actually end up making so much H2S, or you just need so much H2S to start with to actually get the metabolism to run, that H2S is beyond even, you'll see the one data point that's shown down there. Almost nobody believes that particular data point because it already seems so incredibly high given the rest of what the atmosphere is made out of. But you would actually need amounts that were even much, much higher than that. For this to work, and those are inconsistent with at least what we know about the atmosphere. You will notice that there is one model, metabolism C, that's okay with that because it doesn't involve hydrogen sulfide, but the problem there is it involves CO, and you need so much CO to feed that particular reaction that the best constrained molecule almost that we have in Venus's atmosphere, this doesn't agree with at all. So what this means is that life probably is not removing the SO2. And the nice part is if there was life doing this, you would expect to see that. These would be the biosignatures that you would expect to see from that life. And the fact that we don't see them allows you to make a constraint about how much life could be there based on how much power each of the cells is using. There's a sort of minimum cell power there. So there's cell power on the x-axis and maximum biomass density on the y-axis. The Earth aerial biomass, which is very loosely estimated because there's a lot of controversy about Earth's own aerial biosphere, whether it even has an independent aerial biosphere. But it's at about about 10 milligrams per meter cubed. What we can see here is that if we have somewhere near terrestrial maintenance power, we're probably orders of magnitude below that. And for a variety of reasons, which I'll touch on right after this, we would actually expect it to probably have super terrestrial maintenance power requirements because they're trying to run a metabolism in sulfuric acid, which means they must be coming up with some way to protect themselves from that sulfuric acid as well. So these are some of the reasons why I'm a bit skeptical about life being in the clouds, at least life as we know it, certainly. And one of them involves There's this dowel area, this geothermal region that reaches pH of about 0. You see these bacterial mats that go in when the pH is a bit higher. And as the pH is dropping and dropping and dropping, eventually the mats go away. And there seemed to be a sort of evolutionary limit to the acidity that life can handle. And the clouds of Venus are much, much more acidic than that. But the other problem, I think, and maybe a more substantial one, is that the available water is so incredibly low. There's a reason you don't worry about leaving honey out on your counter. You don't worry about bacteria usually growing in that because the water activity of honey is incredibly low. The Earth life limit for water activity is about 0.6, and the water activity in the clouds of Venus, even if they are being pH buffered, the water activity is still well below 0.01. And you can also look at a nice paper by Halsworth in Nature Astronomy that goes into greater detail about this. But let's set life aside for right now. Let's see if we can identify that abiotic baseline. What would we expect to happen if there was no life? So iron and sulfur in the clouds has already been speculated about. Vasily Morose wrote about this in the Venus book, the big black book, if you've ever seen the Venus book. And he speculates in his article here, in connection with the discovery of chlorine in the clouds of Venus, a compound such as ferrous chloride is worth attention. Actually, right above that, he says, however, sulfuric acid does not account for the decrease in the albedo, so this mysterious ultraviolet absorber. At present, there's no conclusive explanation, but two rather geochemically common elements may produce the yellow tinge, sulfur and iron. The idea here is that if you did have iron, you can actually run this particular cycle where you have your sulfur and water. Again, they come together and they form your bisulfite. And your iron can get oxidized. So you knock off an electron from your iron, going from ferrous iron to ferric iron. So iron 2 to iron 3. Your iron 3 can react with the sulfite to produce sulfate, and that restores your iron 2 again. This was actually proposed for certain prebiotic chemistry by the Sutherland group here at Cambridge. Jianfeng Su and others in 2018 have proposed it. This is related to chemistry that was applied, although with somewhat different mechanism, for clouds with iron by Sato et al. And you can also look at, there's a really interesting photoredox chemistry that you can do with this sort of thing that's discussed by Ziwei Liu. It might be responsible for some of the sulfates that we see on Mars. But the fun part is that there's no reason why this chemistry can't work in principle in the clouds. This is still experimental work that is ongoing. But one of the fun things that you can say is, well, let's say that you do form iron sulfates. What minerals does it form? And one of the minerals that it may form is this one here, which is called rhomboclase. This is if you have enough iron and sulfate to kind of have iron sulfate with a sulfuric acid and one water bound to it, you end up with this sort of mineral called rhomboclase. It's seen on Earth, normally in mines that are very sulfuric acid rich. This is what you would expect near the tops of the clouds, where concentration the neat part is that the color actually looks kind of suggestive to the real color of Venus, maybe. What Clancy Jiang, a postdoc, working with Nick Tosca and myself has done is he generated these in the lab and we measured their UV absorbance. And this is the sort of picture that we have is this rhomboclase and anhydrous iron sulfate, which you would get at a particular height in the atmosphere. This, and the anhydrous iron sulfate would ultimately rain down. It wouldn't be stable deep in the clouds. The rhomboclase would not be stable deep in the clouds, but the anhydrous iron sulfate would be, and it might even be stable on the surface. This might explain even some surface measurements which find more iron 3 than you would expect from chemical equilibrium. In any case, we did these measurements. We actually used one of the light sources that we've been using for some of the photochemistry, one of the Star Lab light sources, and put a spectrometer on the other end and measured the absorbance. And ribomyclase and other sulfates seems to fit fairly well with the Venus absorber, except there seems to still be a gap in about the 375 to 425 region, which might require something else. But this at least is a fair candidate for a good fraction of this unknown absorber. I should say that the shaded region is Perez-Hoyos et al. 2017. These are measurements, these are probe measurements of what the Venus absorber is. Akatsuki has an updated version, which I need to compare with the data, but is very, very close to what Perez-Hoyos found. So future work. We could look at other optical properties of these iron sulfates or of the salts or of all these other things. It may be that other optical properties of the clouds already rule out some of these hypotheses. There should be more exploration into the in-cloud observed O2 and surface iron-3. I think there's a lot of interesting work that can be done there. What is the source of iron? I think there's much fruitful work, because even just saying that it's there, how does it actually get there? I think is a really, really interesting question. And there's also a very interesting question, I think, related to this question of if there was a volcanic source of iron, what else is the volcanism doing? What does volcanism say about the atmosphere of Venus, and maybe even about the history of Venus, whether it was wet in the past or whether it was dry in the past? There are some other interesting mysteries. I didn't show this before, but you can see this OCS. It's at about 10 parts per million deep down. It depletes above the clouds, but as you can see by data, and this includes a lot of independent data, the depletion should occur around 35 kilometers. No one's come up with a good explanation for that. There might be an explanation involving a variety of different sulfur allotropes interacting with the OCS and liberating that sulfur. And this is work that's being led by one of my PhD students, Skyla White, in collaboration with myself and Kevin Zonley. The last thing I'm going to mention, and Peter Voigt has started with this, is that a lot of these things will actually be able to be tested. There's a whole bunch of missions that are slated to go to Venus, including the Rocket Lab mission, which will be a probe that goes in to look for phosphine and other signs of life, hydrocarbons, various other things. There is Da Vinci, which is also a probe that will go through the clouds, and this will be looking at isotopes, noble gases, and also water, to try to see whether it can figure out what's happening with the sulfur cycle in there. Veritas will be mapping the surface and looking for evidence of volcanism. There was a very, very interesting recent, I think it was science paper, looking at some archival data that suggests volcanism. Veritas would be looking at this, but in much higher resolution with much greater confidence. There's Envision, an ESA mission, which will also be looking for signs of volcanism, some by mapping the surface, but also some by actually looking at the below cloud and above cloud chemistry, although it won't be going into the clouds to do so. It'll be doing that remotely. And then Venera D, which is the Roscosmos mission, which will do potentially almost everything. But it is a little bit unclear what the future of that particular mission holds. Oh, and I should also mention Shukrayan, an Indian-led mission to go and look at the clouds and atmosphere of Venus as well. So with that, I think that I will conclude, and I will thank you all for your time and attention, and welcome questions.
All right, so I think we may have some questions.
Can I have one?
Yeah.
Hi, Helmut.
Yeah. Hey. Yes, you know, Venus had at least a few 100 million years, and I think 600 or 800 million years ago, resurfacing event.
Mm-hmm.
And how would, or how should I say, I have a very a method in mind where we could, for instance, figure out how much water Venus may have lost from that event on until present. Would this be some support in your study, or how relevant is it? There's another issue, of course, how the water was from the beginning to these event, or you do not know, maybe there were several resurfacing events, but I mean, there's the before, and which is very speculative, of course, but there is a method, I think, where we can figure out relatively precisely or accurate how much water was probably lost from Venus from today until this resurfacing happened. So far, it's not studied in that way, what I have in mind. Mm-hmm. But if you would have such a kind of knowledge, would this support your studies in some way, or?
Yeah, so I've not done a lot myself on Venus evolution, but Sean Jordan has done a fair amount, and Oliver Shortall is especially interested in this, and I collaborate with him fairly closely. One of the PhD students that we're co-supervising, Teresa Constantinou, as I mentioned, is looking at the volcanism and the connection between volcanism and atmosphere. One of the things that she's looking at is a way to constrain the amount of H2O in the mantle. This is relevant for questions that I think are of wide interest to the community, and what you're offering would be of exceptional interest to the community, which is there are these two 3D GCMs that try to predict the fate of water over time. One of them, produced by Martin Turbay and others, suggests that Venus never had condensed water on its surface, but that the water stayed in vapor form until it photodissociated and then oxidized the mantle, and the hydrogen all escaped. And another, led by Michael Way and others, suggests that, in fact, Venus could have had liquid water on its surface. And the way that the clouds form allow you to keep the liquid water there, even though it's outside of the traditional habitable zone. The clouds keep the clouds keep a lot of the light from coming into the surface, because they form predominantly on the day side, and then it's cloudless on the night side, and so a lot of the heat can escape. And this suggests that Venus could be habitable today, but maybe the resurfacing event is what caused all the water to leave. And so maybe the trilobites would have seen a pale blue dot, and then after that, it would have looked like the Venus that we know and love today. And if you could answer how the water escaped with some sort of time resolution to say it escaped, oceans escaped, say 600 million years ago, that would really help to resolve that debate. And it would fit in, I think, also with Teresa Constantinou's models that she's running to see whether the mantle is wet. Because if you did have that much water, it'd be hard to explain how all that water would be lost without at least having a somewhat wet mantle.
Yeah. What I mean, we can discuss this also tomorrow in the separate discussions. But we have a very good idea, really, to get an accurate value how much water, also related with the T2H ratio.
Yes.
From today until the time when the resurfacing happens.
Oh, wonderful.
And this may also somehow exclude probably some, or constrain, let's say constrain how much liquid water, if it was ever liquid, could have been before the resurfacing, because you should see this in some isotope ratios in the atmosphere today.
Great. Yeah, no, I think that would be of significant interest.
But
okay, thank you.
Also tomorrow.
Great.
Maybe we have also some other people who would like to ask a question. So there's Maxime online who has a question, please.
Yes, thank you. I'm sorry, I used probably initially a wrong sign to draw attention to. So my question concerns the temperature profile, which you mentioned. And you take it from the Krasnoselski study. Part of the question I would be curious, to which extent your outcome, your result is sensitive to the details of this profile. And the second part of question, in fact, the temperature profile is not an arbitrary function. So it is self-consistently dependent on the environment, on the heating and cooling mechanisms distributed over the altitude of your atmosphere thickness. And these effects are also connected with the chemical composition, with the reaction. To which extent these temperature profiles and your studies are consistent and mutually connected, and how sensitive your result is to the temperature profile?
Maxime, I think both of those are excellent questions. We've done a little bit of sensitivity analysis with the temperature profile, not so much with heterogeneous chemistry, though. We did nothing with the heterogeneous chemistry, but with the gas phase chemistry, we've done a bit of exploration, mostly looking into the region between 20 and 40 kilometers, and mostly concentrating on the OCS depletion there.
Mm-hmm.
We find that our mechanism for the OCS depletion changes quite a bit. The relative ratios of sulfur allotropes changes quite a bit, but it doesn't seem to be very sensitive for either the CO or the SO2 or the HCl. Those sorts of things don't tend to change all that much. We didn't explore too much deeper, and one of the reasons why is that eventually you get results that are a lot closer to chemical equilibrium, and Krasnopolsky himself and various others have done a lot of very interesting studies into how temperature affects there, with the one exception of right at the surface. Peter Wojtka looked into how equilibrium abundances, both in the gas phase and what you would expect to condense out onto the surface, might change depending on the surface temperature. So if you lower the surface temperature a bit, you can actually remove a lot of your sulfur. If you lower it even more, you can remove your carbon into carbonates. You can do some really fascinating things.
And also albedo probably changes as well with the.
That would be very true.
So it's all so complexly interconnected. So yeah,
yes,
really puzzle.
And that's to the second part of your question is we do, along with a lot of photochemical modelers, sadly, we do just take the temperature profile as a sort of arbitrary profile. It's empirically kind of given and set. As far as I know, there aren't too many models of Venus that that try to take into account the effect of climate. And there's none that do both climate and chemistry that I know of. Sean Jordan is developing a climate model that can be applied for Venus so that we can figure out how the temperature profile changes, but for a very different application. It's actually for moving Venus around different kinds of stars. So if you move Venus around an M dwarf, the photochemistry changes in really interesting about that, which is really interesting. But we just used Venus's temperature profile for all those stars. We knew that that was not an inaccurate thing to do. So now Sean's going back with a climate model to figure out how that temperature profile would change. I hadn't considered actually applying that to Venus and like actual Venus, but that actually probably be a good idea.
Yeah, thank you.
You're welcome.
Maybe I asked the last question, or I have actually two questions. The first quick thing is you didn't mention the Life Finder mission in your overview that is still visible.
Oh yes, it is still there. I can talk about that a little bit more. Yeah, definitely.
Just a bit.
Do you still hear me?
Yes, yes. We were just taking because people would like to finish, I think. But yeah, if you could say a few sentences about the Life Finder mission, I think that would be great.
Absolutely. So the Venus Life Finder mission is a mission involving the collaboration of Rocket Lab, MIT, and some support from the Breakthrough Initiative. The PIs of the mission are Sarah Seeger and Janusz Petkovsky. And I am part of the science team. One of the purposes of this mission, in fact, the primary purpose of this first stage mission, the small stage mission, is to just send a probe very briefly through the clouds. And one of the main things they'll be doing is looking for phosphine in the clouds. It will also be able to look for ammonia, which has been implicated by various other probe data. And it will also be looking for some complex hydrocarbons in the cloud droplets. And this is based on work from Jan Spacek and Steve Benner, who have taken formaldehyde and put it in sulfuric acid and have found a rich and complex organic chemistry that emerges from that, that changes the color of the clouds, might help to explain some of the UV absorber, and also might be observable by this mission. If the mission finds interesting things, there's a real potential for a medium-sized mission and then a large-scale mission to subsequently follow.
Thank you. Do you have a launch date?
I do have the predicted 2027, which is the last that I personally have heard. I should check with Janusz to see if that is still accurate. It seems like it's very close to now. It didn't seem so when this was first proposed.
Okay. Well, I think then we would like to thank maybe the speaker again.
Thank you very much.
And there will be another meeting with the PhD students soon, and then further meetings tomorrow.
Thank you, Paul. It was very nice to hear you talk.
Thanks.
Good evening.